Hey everyone, I'm the DataByte, and today I'm back with more linear regression calculations. Although these examples are using stock market data, you can easily adapt them to whatever dataset you're working with. We're going to write some code that enables you to calculate linear regression lines over moving windows of time. Check out this next animation. We're going to be looking at a rolling window of time, where we're taking 5 consecutive data points and calculating a best fit line using linear regression. We're using the same methods that I discussed in my previous video, so check it out if you haven't seen it already. Today, we're just going to be looking at how the R-squared values differ between these different lines to see if there are any linear trends in stock market data. Remember how you can use the R-squared value to determine how much a linear trend line can describe your data set? Here, we're looking for values as close to 1 as possible, with about 0.7 being our acceptable lower limit. This exercise with stock market data is just for fun. We all know that stock market data can't be described purely with a straight line. There are so many ups and downs along the way. However, it's really interesting to see that there actually are linear trends present if you narrow your focus down to only a few days. Even if you're not interested in the stock market, you can use this methodology to investigate trends in any data set that you're interested in. Today, we're just pulling the R-squared value out of the models to evaluate how it trends over time. But you can also pull out the slope, intercept, or other parameters too. Let's check out the first example. Check my files out on GitHub to follow along, and feel free to pause the video to take a closer look as well. Here, we're actually going to be making these calculations by hand with the sum of squares functions that we discussed in my last video. This is how we do it if we didn't have functions pre-built to help us out. These are the sum of squares calculations that I talked about in my last video that we're going to be using in Excel. R squared has its own calculation here as well. Check out my earlier videos for a more detailed explanation of linear regression if you want to learn more. First, let's look at our dataset. Here, we're just looking at some daily data for Facebook stock. The daily closing prices are all we'll need here for this example. I'm adding another column here called date num. This is just the days numbered in sequential order. Honestly, when I work with dates, it's an easy shortcut for me to just work with them in numerical format. Sometimes the functions that I want to work with don't work well with dates, so I need to end up converting them anyways. Next, we're creating a column for x bar. This is just the average value for x in our dataset that we're feeding to the linear regression model. If you were interested in using this whole dataset to construct a linear trend line, you just take the average of all of the x values that you have. We're doing something else here because we're looking at a rolling 5-day window. Each day has a different 5-day window associated with it, so we actually need to redefine x bar for every row that we have in our dataset. It's actually pretty easy to do with Excel. Start by writing the formula for the first calculation. You can just leave the first 4 rows empty because we don't have enough data until day 5 in our dataset. You can see the formula for this calculation in cell I6 here. When you're done, just hit enter and make sure your first calculation checks out. The average of these numbers is 3, which is correct. Now we need to update the rest of the column. This actually is going to be really quick. With Excel's relative referencing style, this formula remembers the cell references to the parent cell. The next step here is to hover over the bottom right corner of the cell. Your cursor should appear something like this now. All you need to do now is just double-click. Double-clicking will copy the formula down for the rest of the column, keeping the references. Now, if you look at the formula in the next cell, you'll see how the cells referenced for the function just shifted down by 1 cell. Previously, it was cells H2 through H6 that were used for the average calculation. Now it's cells H3 through H7. just one row down. That's because we copied the formula one row down and Excel kept the cell references. The references will shift depending on where you copy the formula. If you copy it one column over, the references will update to one column over, etc. You can use the $ in the cell reference if you want to hold the cell and/or the column or row constant. We don't need to do this for this example. Anyways, we're going to follow the same process to update the rest of the formulas. If this is a new concept to you, I recommend rewatching this part of the video if you get lost, or just playing with Excel on your own. If you're new to Excel, in my opinion, this trick is the major thing to take away from this video. You can forget about Python or R or linear regression. This trick is really powerful in Excel and it will make you really efficient. Anyways, I'll continue with showing you how to create the rest of the calculations. We're going to go a little faster now. Using the same technique, we're creating a column for y bar, which is just the rolling average of your y values in the dataset you want to feed to your linear trendline calculation. Next, we're creating a column for SXX. We are taking the sum of the difference between each individual x value, which is x sub I in the formula shown here, that's fed to the trend line, and the average value for x in the data set that's fed to the trend line squared. This is why we created a separate column for x bar, as we refer to it, and also y bar, frequently for these calculations. We're doing the same thing for SYY, but with the y values now. For SXY, for each individual x and y value in our data set, we're just subtracting x bar from those values and multiplying those values together. We're doing this for each set of XY pairs in the data set that's being fed to the trend line, and then just adding those values up together. Next, we're going to calculate the parameters A and B for our line. Here, B is just SXY divided by SXX. Here, A is just y bar minus B times x bar. Lastly, my calc column here represents the new y value from our trend line. This is where we're using the equation for y hat, the new equation for the trend line. A is just our y-intercept, and B is our slope, or coefficient of x in this equation. We actually only need the sum of squares calculations to calculate values for r squared. I just added the other columns to this explanation so it's easy for you to refer back to later. We're ready to move on now. We have so many other stocks that we need to do these calculations for, so we better get started. You're probably thinking, oh no, I have to type this all over again. Never fear, copy and paste is here. Like I showed you before, what's awesome about Excel is that when you copy and paste something, the formula references will come with you, even when you move to a new sheet. Let's go back and check out what we did before. The date num column are just numerical values. There's no formula there, so copying and pasting them will just keep the same set of values. We just need to make sure that each data set is the same length, so we don't miss anything, but the series will be easy to extend anyways. Everything else that we did was equations. Just like we could double-click the cell to extend it to fill up the rest of the column, if we copy and paste the full data set between tabs, it will keep your references too and adapt them for the new tab by default unless you add in $ or paste it in a special way to change the way the cells are being referenced. By copying the whole set of columns that we made, you can copy and paste them to the new tab. Here, we're pasting all of that information in cell H1, which naturally extends over the rest of the columns and rows that we created. We're just using cell H1 as the top left-hand corner reference for the copy and paste operation. When you paste this data, the formula references should adapt to your new tab, and the calculations will complete again. It's important that the references of your new data sets are the same as what you were working with before. For example, if the closing price on this new tab were actually located in column D instead of column E, the formulas would still use column E for the calculations. If you inserted a new column to create a new column E after column D, the formulas would shift again because you inserted that new column, and they would reference column F instead of column E. The formula references are there to help you. So if you're dealing with multiple data sets and multiple tabs, try and copy your data similarly so you can utilize the full power of Excel. Remember how these formula references are all pointing to column E for the closing price information? If you wanted to perform the same analysis on the opening price data instead of just updating all of the formulas to change the references to column B, you could just copy and paste that data on top of what you already have in column E. You can easily just undo this by hitting Control Z. Anyways, you want to scroll down to the end of your dataset to make sure that all of these formulas copied completely. Even if they didn't, you can just highlight the last row that they copied to, and then use your cursor to hover over the bottom right-hand corner of the cells that you selected, and just double-click to extend the calculations. The series that we created in column H should update as well and increment by 1 each time. I'm just going to flash the beginning of the other tables so you can see the initial calculations too. As you'll see, these R-squared values will match the values that we'll eventually calculate in Python and R as well. Here it is for GOOG, for Google, Amazon, Netflix, Microsoft, and Apple. You can make a plot to combine this data together and compare the R-squared values. The values range between 0 and 1, which is normal for an R-squared value, so that's good. And they appear cyclical. Interestingly enough, there are periods of decent linear behavior in stock prices. Look at how frequently you see the R-squared value above a 0.7. Remember, this is for our moving window of time, so this is only looking at 5-day periods. Additionally, there are actually a few times where that R-squared value comes pretty close to a 1. That took me by surprise. Next, we're going to use Python to do the same thing. This time, we're going to use the stats models package, so we're not recalculating all of those sum of squared functions. First, we're taking care of import statements. What's new from the previous video is that we're going to be using Plotly for plotting up our data. To help make things more efficient, I'm adding a loop here to just add the additional text to my file names. I'm reading these files in as data frames with the readCSV function, and then using a loop to combine them into a list of data frames. We're adding a column for our squared value in each of these data frames to store the results of our next calculation. I'm doing it in this for loop here, but we could also just do it in the next for loop as well. You can see how the files are importing below too. Now for the loops. The first for loop is looping over each data frame in the list that we created. Then, within each data frame, we're using the next for loop to calculate the R-squared value over those 5-day periods and storing it in the data frame. I have some comments in my code to help make sure that the calculations are working correctly, and I'll walk you through how I use them. Using the first break and the 2 print statements, leaving everything below as comments, you can see how the X and Y values are being assigned. We're just taking the first 5 rows of the data frame here for the first trend line. On the next iteration of the loop, we'll be taking rows 2 through 6, and so on. Now we'll run this block of code again, this time commenting out those print and break statements we had before, and uncommenting the next set of print and break statements. This time, we're checking to see what the R-squared values are that our model calculates. Like I mentioned in my previous video, the add constant function is needed with the OLS function here because we're not automatically assuming that the intercept of the linear regression line goes straight through the origin. Remember, the sequence of the data frames in our list is the same as the sequence of the paths in our list. So for example, that 0.283 R² value is for Facebook stock. As you can see, these values check out with what we calculated in Excel, so we're good to move on from here. Finally, we're adding these values to the data frames and storing them in that R² value that we created. We can show the tails of our data frames after these calculations have finished to make sure that the final values match what we have calculated in Excel as well. Now, we've successfully added a column to our list of data frames that gives us the R² value over periods of 5 days. Checking out the tail of each data frame will give you more information to show you that your indexing references are correct, and you can check these with what we just did in Excel as well. Now we're ready to plot our data. We're using the Plotly library here and using a for loop to add a new trace for each stock in the dataset. You can see that the R² values seem to oscillate between 0 and 1, which is the correct range for R² values, so we're good there. Although the lines look a little crazy, it's interesting because the stocks tend to move together for the most part. Like we already saw, there are a number of periods in time where the R² values come very close to 1, and the behavior, interestingly enough, appears almost cyclical. With Plotly, we can zoom in too, and our cursor can display additional information if we want it to. For example, between days 50 and 52, approximately April 4th through April 12th, 2022, most of these stocks were exhibiting very linear patterns in their closing price data. This is interesting because although day-to-day changes in stock behavior do appear random, this randomness somehow gives rise to almost cyclical trends of on and off linearity, where the linearity of these trends between stocks appears pretty consistent. Next, we're going to do the same exercise, but this time with R. We're going to go much faster here, so feel free to pause the video or just check out my GitHub files if you want to take a closer look at the code. Plotly is the only library I'm importing here. This is just for plotting. Like I did in Python, I'm writing a for loop to help me create a list of paths. This would get tedious to write if I have a lot of files or if they were hidden somewhere deeper on my computer. If you're working with multiple files, it's convenient to have a consistent naming convention so that you can do this too. I'm just using the lapply function to create a list of data frames to iterate over. Just like I did in Python, I have two for loops. The first for loop is used to cycle through each data frame in the list. Here I'm adding the R² column to the data frame in this for loop. The print statement is just for printing the number of the data frame that we're on, so we know we're hitting all of them. To check the output of this for loop, you can add some print and break statements to check out the results. I already explained this process in the Python section, so I'm not going to cover it again here. The next for loop is going through each data frame row by row. We're only interested in using sequences of 5 rows for the input into the linear regression function. Just like I showed you in Python, you can do something similar with print and break statements here too to double check your code. After creating a linear regression model, you can then add the R² value back to the data frame. Remember, we start adding the R² values to the data frame at row 5 because we're interested in looking at linear trends in the data over 5-day periods. Each time the for loop is incremented, we're just moving the window. Now we're ready to plot the results. Like we did in Python, we're using a for loop and using the add trace functionality to add a separate line to the visualization to represent each stock. In a way, these plots look like some children just grabbed a bunch of crayons and went to town. But when you zoom in, you can kind of see some cyclical patterns of linearity. Here are more peaks of linear behavior around day 60 and day 70, for example. These periods correspond to the time frame between April 19th and 25th, and then May 3rd through 9th, 2022. In one of my next videos, I'm going to dig deeper into this distribution of linear behavior in stock prices. So if you're interested in seeing the results from that, stick around. We covered all of these concepts before, and we applied them in this video with a data set of about 6 stocks, where we were looking at how linear trends and their closing prices varied over time, over 5-day periods. This time, we learned how to calculate a linear trend line ourselves in Excel using the sum of squares functions that we covered before. We also used Plotly to check out a few examples in R and Python. If you're interested in working with the code more, check out my GitHub page where you'll find all of the examples that we covered today. Thanks for listening! Like and subscribe to my channel. See you next time.